Consider a camera recording two musicians practicing their acoustic guitars at the same time. While the camera has no trouble seeing each guitar separately, the camera microphone can only hear a mixture of both guitars. Even worse, the microphone is susceptible to unwanted sounds such as room echoes and ambient noises. But what if we can make our camera see the tiny vibrations of each guitar? Then we could record both guitars separately while being insensitive to the other guitar. And to the ambient noises. But imaging such tiny vibrations poses two major challenges. Firstly, the small vibration amplitudes require a powerful zoom lens even for nearby objects. Secondly, the frequencies of speech and music are too high for a regular camera and require an expensive high-speed camera, not to mention the high-power illumination required to compensate for the short exposures. In this paper, we propose a novel dual-shutter imaging system for sensing low-amplitude, high-frequency vibrations. Our method can sense multiple points simultaneously and can also support object motions such as the natural motions of a guitar player. To sense minute surface vibrations, we illuminate the vibrating surface with a laser and image the resulting random interference pattern called speckle. The image speckle pattern is highly sensitive to the surface vibrations, which cause it to shift in the image plane. Our system recovers these 2D speckle shifts at high speeds in a bandwidth-efficient way. So instead of using a high-speed camera, our system simultaneously captures the scene with two low-speed cameras equipped with rolling and global shutter sensors, respectively. While the rolling shutter camera captures frames at only 60 fps, the individual rolls of the rolling shutter are exposed one by one, sampling the speckle at a high frequency of 63 kHz. But having these 1D measurements of the speckle pattern is not enough to recover the 2D speckle shifts. And this is where the global shutter camera comes in. The global shutter camera provides reference frames of the undistorted speckle pattern, which can be used to decode the 2D shifts from the 1D rolling shutter measurements. In this experiment, we record the vibrations of a speaker membrane playing a music file. And here, our system records both speakers at the same time while each speaker is playing a different audio file. While the microphone records a mixture of both speakers, our optical system captures each speaker separately. We can also record the indirect vibrations of a chip's back reacting to a nearby sound source with higher fidelity than previous methods.
Mary had a little lamb whose fleece was white as snow.
Additionally, we can analyze the vibrational modes of various objects by measuring multiple points on the object's surface and identifying the individual modes from the measured point's vibrations. Finally, when recording musical instruments, the natural movements of the player cause a large drift of the speckle pattern. But our system handles such object motions and recovers the high-speed vibrations of the instrument. Or several instruments as seen in the introduction. Please visit our project page for more information and additional results. Thank you.